Okay, hello everyone. In this lecture series, we are going to discuss this paper, Core Paper 4, that is your waves and optics. This paper has 4 units. In Unit 4, Fraunhofer diffraction and Fresnel diffraction. All the topics we are going to discuss with detailed note. With detailed note for your exam. For your exam. These lecture videos are very much helpful for BSc Physics Honors and pass students. Okay. So let us start. First, we are going to start Unit 1. Here in Unit 1, these topics are there. Separately, I have been written in the slide over here. Here you can see format principle, reflection and refraction at plane interference, metric formulation of geometrical optics, cardinal points and cardinal planes of an optical system, idea of dispersion, application to thick lens and thin lens, Ramsden and Huygens eyepiece, and wave optics topics. Okay, in this class, we are going to discuss this topic, format principle. So let us start. Format principle is also known as least time principle. In your exam, maybe it will be asked to discuss about least time principle instead of format principle. You should uh, remember that format principle also called as least time principle. Here is the definition. Format principle states that light travels from one point to another along that path along that path in which it will take minimum or least time. This is the statement by format. So if I'm going to consider the 2 points A and B, suppose A is the source point. Here at A, source is there, source, light source. So the light source or light travels from A to B along that path in which it will take minimum or least time. Here you can consider these possible paths. The light can travel along path 1, along path 2, along 3, or along 4. But here, according to format principle, light will travel along that path. It will take the minimum or least time. So if I'm going to compare these paths, then we can found this path number 2, which is colored by red. Along this path, light will take the minimum time. So according to the format principle, light will travel along this path, along A to B, along path 2. That means along straight line path, along straight line path. So here we are going to prove this statement with a simple mathematics, and we are going to get the final expression, that is your that will be called as your mathematical representation of format principle. Okay, here it is blinked, means along this path we are going to prove along this path light has to travel, not along path 1, 3 and 4. That we are going to prove over here, or so called mathematical representation of format principle. As per statement, for homogeneous and isotropic medium, this one, A to B dt will be minimum. That means light will travel along that path in which it will take the least time according to this format principle. A to B, that means from A to B, the total time, if I'm going to integrate all the time at the time of motion from A to B by any path, suppose, that should be minimum according to format principle. So here dt is the small time. We know that the time is nothing but your displacement by the velocity. So here instead of dt we can write ds by v. So here v is the velocity of light in a particular homogeneous and isotropic medium, that can be represented by c by mu, where c is your velocity of speed of light. This is the source position. Okay, speed of light, and mu is the refractive index of medium, which are both are constant. So this denominator part is the constant. That implies this can be written as, this expression can be written as, this denominator part is constant, taken this side, multiplied in RHS with RHS. So it is written as into multiplication into constant. This is the constant. Okay. So here we found that implies the total distance traveled by the light from A to B. This mathematics mean the meaning of this mathematics means the total distance traveled by the light from A to B is equal to minimum into constant. You just imagine. You just imagine when this will satisfy. That means left hand side is the total distance traveled by the light from A to B will be equal to minimum into a constant. That means from the figure it can be found that here this can be possible. See, this is the constant. So along which path it will be minimum, or along which path the right hand side will be minimum, because this is the constant. If we are going to compare path 1, 3, 4 with 2, then only the path 2 will be give you the minimum value. So here we can found A to B integration ds, that means total path traveled by the light from A to B will be equal to minimum. When it will possible? It will possible when it will move along the straight line path. Okay, or along path 2, whatever we can visualize from this figure. Hence, if it is minimum, if the right hand side is a minimum or one type of constant direct straight line, then del of differentiation of left hand side, del of A to B integration ds will be equal to 0, because del of minimum is nothing but 0. So this expression is nothing but called as equation of Fermat principle mathematically. That means this equation represents the Fermat's principle mathematically. Okay, this is the statement. From this statement we derived another mathematical expression which is also called as the Fermat principle. So here we found that the light has to travel along that path in which it will take the minimum or least time. If it is so, then that path will be the straight line from one point to another. Okay, so this is all about Fermat principle. If it will ask in your exam, it will ask 2 mark question or 1 mark. 1 mark means just write down the statement of the Fermat principle. You have to write this statement and you have to write this equation or this equation. Or if it will ask 2 mark, that means you have to write these steps also. Okay, so here I'm going to stop today's lecture. Next lecture we are going to discuss laws of reflections by Fermat principle. We have to prove the laws of reflections by Fermat principle. Thank you so much for watching this video. Thank you.